Good morning. Today we will discuss about interference in thin films. In the last classes we have discussed interference and the theory of interference fringes and how the Fresnel's two mirror arrangements produces interference pattern on the screen. So now we will discuss about interference due to thin films. So it was Newton and Hooke who observed and developed the interference phenomenon due to multiple reflections from the surface of thin transparent materials. That's why we call thin films. It is transparent material, but at the same time it is very thin. Everyone is familiar with the beautiful colors produced by a thin film of oil on the surface of water and also by the thin film of a soap bubble. So we have already experienced this in our daily life. So Hooke observed such colors in thin films of mica and similar thin transparent plates. Newton was able to show the interference rings when a convex lens was placed on a plain glass plate. Young was able to explain the phenomenon on the basis of interference between light reflected from the top and the bottom surface of a thin film. It has been observed that interference in the case of thin films takes place due to reflected light and transmitted light. So there are many physicists who observed interference pattern in different occasions. So Hooke observed colors in thin films of mica and similar thin transparent plates. And Newton observed these interference rings when a convex lens placed on a plain glass plate. And Young could explain the phenomenon on the basis of interference between light reflected from the top and bottom surfaces of a thin film. So the reflected light and the transmitted light can able to interfere and produce interference fringes. So these people have observed these interference fringes or interference pattern in different occasions. Okay, so now we will discuss about the interference due to reflected light from a thin film. So there is a possibility of interference due to transmitted light also. Now we will discuss that due to reflected light from a thin film. So for that we will consider a transparent film of thickness T and refractive index mu. So here in this figure we have shown a transparent film of thickness T. So this is this top line and bottom line. This represents a thin film of thickness T. Actually this thickness is very small, but we have exaggerated this figure in order to show this thickness T. And this film have a refractive index mu. Suppose a ray SA, here it is S and the end point is A, is falling on the top surface of the film at an angle. Okay, so we have drawn normal to the surface, so this is the angle of incidence. So this is the incident ray. And this ray is partly reflected, so this is reflected along NT and partly transmitted or partly refracted along AB. Okay, and at B what happens? At B, part of this ray is transmitted and part of this is reflected along BC. And finally this ray emerges out the film as CQ. Okay, so seeing the path of this incident light, this falling on this thin film and part of this reflected to this outer film and part is refracted and a part of this refracted again transmitted and a part of this is reflected and again this is reflected back out to the film. Okay, So we have to find out the path difference between these two rays, AT and CQ, because this is going to interfere and produce interference pattern. So we have to find out the path difference between this AT and CQ, then only we can know whether this will produce bright or dark pattern of fringes due to interference. So we can calculate the path difference between this AT and CQ. For this, draw CN normal to this AT. So we can draw CN, and similarly we can draw AM, which is normal to BC. So the angle of incidence is I. So this angle is angle of refraction is R. Also produce CB, means CB to meet AE, that is extend the CB line to meet at point P, which is the extension of AE. So AE meets at P when it extends, and similarly CB meets B when it extends. Okay. So this is the angle of refraction, and so this is the this side and this side. Sorry, this is angle of refraction and this is angle of refraction. This is equilateral triangle. So this side and this side are equal. So this angle and this angle are equal. So this is angle of refraction and this is angle of refraction. And this is angle of refraction. That is angle CAM is angle of refraction R. And this is angle of incidence I. Okay. Here angle APC. Angle APC means APC, which is R, which we have already said now. Now the optical path difference. So we can see from this figure, this ray SA, this travels around AB, BC, CQ. But the first on this ray travel from this and travel around this. So the path difference between, so the total path traveled by this rays, the second rays this, that is SABCQ, and this is SANT. Okay. So we can calculate the path difference between these two rays. So the additional path traveled by, we have drawn a normal from this point to this curve. So up from this point, that is NT and CQ are equal. That is from these points onwards, their paths are equal. And this path is equal for both the rays. So the additional path traveled by this ray is AB plus BC, and the additional path traveled by this ray is AN. Okay, so we can calculate the path difference as X is equal to mu into AB plus BC, because this region is inside the film. So inside this region we have a refractive index mu. So we have to consider this refractive index also. When for air, the refractive index is 1. Okay. So the additional path is mu into AB plus BC. This inside the medium. Mu into AB plus BC minus the additional path on air is AN. So this is the path difference between this ray and this ray. Okay. So we have to find out this X. So first we can check what is mu. Mu is by definition is sin I by sin R. This is the sine of the angle of incidence and sine of angle of refraction. So which is from this figure, take this triangle ANC. Triangle ANC. We can, I have shown here, yeah, triangle ANC, in which sin I is AN by AC. I have wrote down it here AN by AC, and consider this triangle ACM. So this is the angle of refraction R. So from this triangle, sin R is equal to CM by AC. Okay. So CM by AC. So from this sin I by sin R is nothing but AN by AC into AC by CM. So which is AN by CM. So this is how we obtain mu as AN by CM. So we have got mu is AN by CM. So from this AN is equal to mu into CM. So we can substitute instead of AN mu into CM. So if we put back this mu into CM instead of AN here, we will get X is equal to mu into AB plus BC minus mu into CM. So mu is common in both the terms. So we can take mu. Mu outside. So mu into AB plus BC minus CM. So here we can see this triangle. In triangle APB, AB is equal to BP. AB is equal to BP. I have triangle ABP, AB is equal to PB. Okay. So AB plus BC can be written as PB plus BC, because AB is equal to PB. So AB plus BC can be written as PB plus BC, but PB plus BC is nothing but PC. Okay, so this is PC. So we can write mu into PC minus C. Okay, but PC minus CM is nothing but PM. So we will get X is equal to mu into P. So we have got the path difference in terms of mu and PM. So if we calculate PM, we will get the path difference. So in the triangle APM, this triangle APM, cos R is equal to, this is R. So cos R is equal to PM by AP. Okay, PM by AP. Here PM is equal to AP into cos R. So from this expression we can write PM is equal to AP into cos R. But we can write AP as AE plus EP. So AE and EP are equal, which is nothing but the thickness of the thin film. So we can write T here, so which is 2T cos R. So we get PM as 2T cos R. So the path difference X can be written as mu PM as 2 into mu T into cos R. So this is the path difference which is produced. Path path difference between the light rays reflected from the surface of a thin film. Okay, so this equation in case of reflected light does not represent the correct path difference but only the apparent. So this may not be exact. This represents an apparent difference, path difference between the reflected rays. It has been established on the basis of electromagnetic theory that when light is reflected from the surface of an optically denser medium or air medium interface, a phase change phi equivalent to a path difference lambda by 2 occurs. Okay, so when light is reflected from the surface of an optically denser medium, its phase changes by a quantity pi, which is equivalent to a path difference of lambda by 2. Okay, that means a complete cycle represents 2 pi or lambda. So therefore, the quantity pi is equivalent to lambda by 2. Therefore, the correct path difference in this case can be represented as 2 mu t cos r minus lambda by 2. That is a phase change, an additional phase change pi is occurring there, or lambda by 2 is occurring there. So this is instead of 2 mu t cos r, this is 2 mu t cos r minus lambda by 2. Okay, if the path difference x is equal to n lambda, where n is varying from 0 to 0, 1, 2, 3, etc., constructive interference takes place and thin film will appear bright. So we can write the condition as 2 mu t cos r minus lambda by 2 is equal to n lambda. This is condition for bright fringes. So in terms of 2 mu t cos r, this becomes 2n plus 1 lambda by 2. And if the path difference is 2n plus 1 lambda by 2, wherein n is equal to 0, 1, 2, 3, etc., destructive interference will take place and the film will appear dark. So from this equation we can write this is equal to 2n plus 1 lambda by 2. 2 mu t cos r is equal to n plus 1 lambda. Okay, here there is 1 by 2, 1 by 2, this will cancel. 2 mu t cos r is equal to n plus 1. So these are the conditions for the film to be bright and dark. Okay, here n is an integer only, therefore n plus 1 can also be taken as n. So n or n plus 1, it represents an integer, so no problem in that. Therefore 2 mu t cos r is equal to n lambda, where n is varying from 0, 1, etc. It should be remembered that the interference pattern will not be perfect because the intensities of the rays AT and CQ will not be the same and their amplitudes are different. The amplitudes will depend on the amount of light reflected and transmitted through the films. That is, the interference pattern will not be perfect. We may not get a perfect interference pattern because the intensities of the reflected lights will not be the same and their amplitude may be different. The amplitude will depend on the amount of light reflected and transmitted through this film. It has been found that for normal incidents, about 4% of the incident light is reflected and 96% is transmitted. Therefore, the intensity never vanishes completely and perfectly dark fringes will not be observed for the rays AT and CQ error. But in the case of multiple reflection, the intensity of the minimum will be 0. So in the case of destructive interference, there may not be completely dark fringes because in the transmitted light 4% of the light is reflected, only 96% is transmitted. So there may have such variation in the color of the film. So now we can know colors of thin films. When white light is incident on a thin film, the light which comes from any point from it will not include the color whose wavelength satisfies the equation 2 mu t cos r is equal to n lambda. So this is the condition for destructive interference. So any reflected light which satisfies any reflected light from the thin film which satisfies this condition 2 mu t cos r is equal to n lambda, that color will be absent in the thin film. Okay, therefore the film will appear colored and the color will depend upon the thickness of the angle of thickness and the angle of inversion. So from this equation it is clear that this is depending on the values of the thickness of the film and the angle of incidence, the angle of inclination. If R and T are constant, the color will be uniform. If these values are constant, then this will be the film will have a uniform color. In the case of oil on water, different colors are seen because R and T vary. So we have seen the oil, when oil is spread on the water surface we can see colors. Similarly in soap bubble we can see in colors. So these are because of this thin film reflection, and this colors appears because of this condition, that is whether it satisfies this equation or not. This is about colors of thin films, and we have discussed today interference due to reflected light.